So, anybody trying to do that cool value trick from before, it won't work. I want to show you a more general thing that always works. So, here we are. Cut out of there. So here's our window. I'm going to go in and take that 40 out because we don't need that 40 anymore. That was for the last 40 million people. It's going to be more than that now. So if you hit graph and you try to run the value command at this point, second trace, value, you guys have all figured out it's 23. 23 years after 1990. You figured that much out. So you go 23, enter, invalid. And here's the problem with value. It only works in the window your TI can see. Why? I have no good answer. It's a stupid limitation of that function. So, there's two ways around this. One way is to bump the window out so that it contains x equals 23. That's one way. So, but it sounds like you guys don't like messing with that window thing. But I'll show you how to deal with that. So, you can go to your window button and just make your x max big enough so that it contains 23 in it. That's one way around it. What's that?
Let's just hit that.
Oh, that works just fine. That works just great. So you can make it say 25 or 24 or something along those lines. Press graph again. It's going to go off Y. That doesn't matter. You can also make the Y bigger to catch the line as it goes off the screen, but you don't have to. Now you can run that command just fine. Ba-doom, ba-doom. 23. And there you go. Now you don't see it because it's off the chart vertically, but for whatever reason, you have to adjust the window to catch that X value. I don't know why. It's just a limitation that the TI put in there, and for whatever reason, it's there. Are we happy with that? Can we live with that? Limitation? So you want to just leave it at that? There's another way that always works, but if you're happy with this, I'm happy with this. Cool? If you want to see some other way that doesn't involve messing with windows, just grab me after class and we'll go over it. Yeah? Yes! Absolutely! We could have also done it algebraically. But I want to answer Tom's question about why he's getting an error. So yeah, of course, you guys do realize we could have just as easily put 23 into our equation and figure it out, yes?
Yeah,
of course! Absolutely, of course, please.
So if it's easier for us just to do it like that?
Yes, do it that way. I'm not trying to say you have to do it this way or just whatever's easier. Whatever's easier. I'm trying to give you more tools in your toolbox. Yeah, if algebra is your strength, go with algebra. Trey, go.
I have no idea how to do this.
How to do that value thing?
You know, I was trying to do the intersect one.
Oh! Email me. I'll send you the little booklet that walks you. It's a 95, so you've since forgotten. Don't worry about it. Perfect. I'll send you a booklet that walks you through this. I don't want to get hung up on the keystrokes, but I'll send you the booklet so you have it. Cool? Now, here's an issue. And this is where I have to think like a statistician and not a mathematician. All right? And I love the fact that we just, you know what? Let's do this. Let's do this. Go back to your stat. We're recording, right? No. Do we? Is that red? Yeah, that is. Go back to your stat. Go back to your stat list. Okay, go back to your stat list. Edit. And what I want you to do is, at the bottom of your list, I want you to add the point 23 and the point, what did you say it was? 57.25, is that right?
Yes.
57.25. So that's the last point we just came up with. Okay? Now please go and turn your plot back on. Remember we've turned our plot off before? So go turn your plot back on. So you have your best fit line. You're going to turn your scatter plot on. And it's going to look the same, except you're going to have an additional point now. And the additional point is your prediction point you just came up with. Yeah? Your prediction point you just came up with. Press zoom 9 again. Zoom 9. There they are. Now look, the window looks a little different now. It's a little different than it used to look. Here's this is your old window was essentially right here. But this is your predicted point. Notice it exactly goes through the line. It exactly goes through the line now. Yeah? Hopefully that makes sense. It has to go through the line because it's on the line. We used the line to get that point. So therefore, it should be on there. Okay? Now, here's the question I have. Knowing that, how do you feel about this? How do you feel about this? Right now, according to the CDC, there are actually 48.2 million uninsured Americans.
That's an estimate.
So is ours, isn't it? So is ours. So whose estimate do you believe? Do you believe the CDC's estimate of 48.2 million?
No.
Or do you believe our estimate of, what did we say, 57.25?
Ours,
We believe ours. Why?
because that's the government.
Because that's the government. Wow. Because that's the government. Okay, that's a damn good answer, Kelly. It's a damn good answer. Show your sources, government. Well, here's where the CDC got their data from. Just so you know. So if you look at the horizontal scale, this only goes up to 2007. They haven't updated it since 2007, but you can see the pattern in the uninsured rates. We have data from 92 to 2000. So we've got 92, 94, 96, 98, and 2000. So if you go straight up from that, essentially this is where our data goes. Now do you see what the data is doing there that our data doesn't do? Yeah, our data does go up and down, but it doesn't look quite as spiky as that. And that's because I intentionally left some of the data out. And then, what appears to happen as we get through the year 2000? It starts to level off a little bit. The slope isn't quite as steep as it is in here. It begins to level off a smidge. Now, it's constantly changing. I mean, look at it from here to here. It's almost linear, perfectly linear from here to here, and then spike, then a drop, then a spike, then a drop, then a spike, then a drop. So when we do these estimates, these average estimates, we're assuming something about the data. And that big thing that we're assuming is what?
That it's accurate?
Well, that it's accurate, and more importantly, what's it going to do in the future? Keep doing what it's doing right now. The trick was, we built our estimated line, on what appears to be slightly oversloped data. Which means that the further we get away from our data set, what's going to happen to our estimates?
Be higher?
They're going to be higher than they should be. Much like if we chose to build our data set back here, it's going to be slightly under. Over, under. The kicker is, there's always going to be uncertainty in any measurement you do this way. It's a best fit line. But the assumption is, when we go out 23 years from the beginning of our data set, we have to accept the fact that there is uncertainty in the number we've reported. There's uncertainty in their number too. I'm not saying there's not, Amber, you're right, there is uncertainty. But both of our estimates have uncertainty. The question is, which one is probably closer to the truth? And not to disagree with you, I love your reasoning, the government's got to be suspect. Their estimate is probably better than ours, because theirs was most likely based on a random sample taken in 2013. Not taken late as 2000, like ours was. We have 13 years of change that is unaccounted for in our data set. Now, some of you might go, I don't really care about this. Some of you might, and I offer this as an impetus for why you should. This explains why the housing crisis happened. People ignored the fact that trends can change. And they assumed that the trends would continue exactly as they always have. Oh, my house doubled in value from 2000 to 2002. It doubled in value from 2002 to 2004. Hell yeah, it's going to double in value from 04 to 06. Nobody promised that. Nobody promised that. Those kinds of bets are gambles. Those kinds of investments are gambles. You could lose something from that, as many people found out the hard way. So when you assume behavior continues, you're playing a slightly dangerous game. That slightly dangerous game is called extrapolation. Extrapolation is when you go outside of a data set and you use the data set and the model you've gotten to predict what's going to happen. You always have to assume some potential error when you do that. There's ways to measure the error, and that's the program I'm writing for you guys right now. It's not done yet. I want to share it with you here momentarily. It's not done yet. I'm getting there close. But there's going to be an error in your estimate because, I mean, think about it. All that variation in the data points, we have the best fit line. Well, that doesn't mean it's the perfect fit line. It's the best fit line. Both components of that line, the tilt and the up and down, the y-intercept and the slope, are both off a little bit. You have to account for that offness in any prediction you make from the line. And that's why one of the programs I just gave you is called RegConf. It's kind of a weird little name. If you look at the programs, it's called RegConf. right here. Somewhere down there in your list, I gave it to you. Now, the idea of this one, it stands for regression confidence interval, but because these things occupy 1982 technology, I have 8 letters to use, so I have to pick them very wisely. When you run the program regconf, it asks you, first of all, have you run the regression? We already have. A regression is what you guys just did in the 1var stats, you know, the lin reg. You run the regression, so you hit yes.
Mine gave me this whole one.
Say that again. Press enter to make it run. Okay? Now it says, what input do you want to use? So what you would do is you'd put in your 23. That's the input you want to use is your 23. And then press enter. And it will come back. Based on the data that you just regressed into your formula, the answer you gave me was it was 57.5 million uninsured in 2013. Allowing for the uncertainty, you really shouldn't say it's exactly 57.75. You should say it's at least 55.4 or at most 59.1. So in other words, what it does is it takes that single number and it puts what's called a margin of error on that. And it gives you a range of values, which is far more believable. Have you ever watched them track a hurricane when they're trying to do predictions of where hurricanes are going to go or tropical storms? They show the track, where it is right now, where it was the night before, the night before, the night before. It usually follows some kind of a spiral. And then as they get like tomorrow, Thursday, Friday, Saturday, what happens to the track? It starts doing this. This program takes care of the further you get away from the model, the wider those intervals get. So the larger number you put in for an input, the wider apart they're going to get. That takes care of a little bit of what's called the uncertainty. It does not take care of the fact that you built your model based on 5 points 13 years before or more. That's the problem. You got to be real careful. I mean, you can go back to 1981 and go, okay, from 81 to 82, things looked awesome. Okay, you can build your model off of that. And here it is right here. That's what your model's going to look like. Are you going to be anywhere near where the truth is now? No, that's the problem. You have to be wise about it. I'm not saying this isn't roughly linear data. I mean, you can argue that's slightly linear. But you'd also want to use all those data points in your regression, not just 5. You see what I'm getting at, friends? We'll deal with that more momentarily. Please!
I don't have that red comp program.
I haven't given it to you. I have to share programs with you. Yep, and we'll do it at the break. It's not working 100% correctly yet. It works great for certain data sets and not great for others. So I'll ask you to use it from time to time, but I have to clean it up first. Right now, it works great on this data set.
Mine ended up different from yours, so
I think I know why. Don't worry about that. Don't worry about that. I think I know why, though. Okay? But that's the problem. The problem is, yes, in 2013, there are 48.2 million Americans. And I put R in quotes because we don't actually know how many there are. That's the estimate. We said 57.75. Lord only knows what's going to happen next year, or this year, because now that number should theoretically drop significantly. Should theoretically drop significantly. It's already dropped by a couple million. If you think about that, it's dropped by a couple million already. I mean, that's sizable. Here's 48.2 million. Take 2, 3 off of that already, and not only what's going to happen once that freaking website works. So, you know, that's the idea. You can't just blindly accept a model over time without actually demonstrating that it's doing what it should do. Fair enough? Now, some of you still might not care about uninsured people in the United States. That's totally fine. Some of you might care about this instead. This is as much data as I could find. Mount Bachelor's full-day adult ticket price.
It's over 70 now.
Well, that's the thing. Let's see if what the price is now is fair based on historical trends. Here's what I want you guys to do. Here's what I want you guys to do. Let's input this data into our TIs. Yes, use that. Basically, you can use that booklet, but you're going to have to use different data. Let's make a couple of concessions. Let's make a couple things to make life easy for ourselves. Don't type in 1983, 84, 85. Why don't you call that 3, 4, 5, 6? Make it easier for ourselves, less typing. So 3, 4, 5, 6, 7. You can totally do it with the full years. Let's make life easy, though. So 3, 4, 5, 6 all the way down. For any year with an unknown ticket price, leave that out. You don't want to put in 0. That would imply that Bachelor didn't charge you for using the lift that year. Nice to think about. Not going to happen unless you're a backcountry skier. And then 07 would therefore, that would be what? 27, I guess? Yeah, 27. So 3 through 27 in your lists, but omit 21 and 23, it looks like. And then put the Y values in dollars. Oh, I should put that. I should put that in. Sorry, guys, I'm going to put the dollar symbol so you understand. I mean, I think you probably figured it out. There you go. Bigger. My little man skiing down Marshmallow. Russian. You got to witness his cousin fall off the ski lift. Broke her arm right in front of him.
Oh, no.
That was great. He's like, Max, be a backcountry skier with me. Don't have to worry about a ski lift. Yeah.